In your last chem study lesson, you learned about the existence of radioactive or unstable nuclei in some of our atoms. Specifically, you looked at uranium and the alpha decay that it undergoes, and noticed that uranium was such a large nucleus that it couldn't hold together anymore, and the net result is that it spit out a piece of alpha radiation, which is two protons and two neutrons, and along the way became a smaller nucleus. The existence of unstable nuclides is actually a relatively common thing. Scientists have what is called a chart of stable nuclides, and it is essentially a plot that shows number of neutrons versus number of protons, and they have simply logged which of these things are stable, meaning that they're not radioactive, and which of these things are unstable, meaning that they undergo radioactive decay. Schoology had today for you a sheet to print that had this chart of stable nuclides if you wanted to, or for the purpose of taking some notes, you could very easily just grab a piece of paper, draw a quick sketch that looks something like this, because there's going to be a digital version of the chart of stable nuclides available to you via Schoology. But for the sake of having a few notes about what to do with that, you're going to want to write a couple things down. Like I said, even if it just goes on a very, very simple sketch of a neutron versus proton graph, which just has kind of some little speckles on it to represent the stable nuclides. So when you're looking at this chart of stable nuclides, you read it kind of like playing Battleship. Like if you want to know if the nuclide that has 60 neutrons and 60 protons happens to be stable, you just go to the point 60, 60, and you find out that there isn't a little blue dot there, which means that if you had an atom whose nucleus had 60 protons and 60 neutrons, the nucleus of that atom wouldn't be stable, it would be radioactive, and it would undergo some type of radioactive decay. While there isn't a hard and fast rule in terms of looking at a nucleus and what's inside and predicting whether it's going to be stable or not, there are some general observations that scientists have made. They have observed that for nuclei less than 20 protons, so anything calcium or smaller, a stable nucleus will have about 1 neutron per proton. For atoms that have a larger nucleus, more than 20 protons, you'll notice that the band takes a little tip in an upwards direction here, and it takes about 1.5 neutrons per proton in order to have a stable nucleus. In terms of reading this thing, it can be a little hard when working on paper to decide where exactly those points are. So if you return to Schoology, you'll notice that the first link on Schoology is now the chart of stable nuclides. And this thing is actually just a Google Sheet that's a little bit easier to work with if you leave Schoology. And once this thing loads, I can show you that you can actually point to any one of the little dots on the chart here, and it will tell you how many protons and how many neutrons are associated with that little dot. So there's the whole chart. You can zoom in and out if you need to see it better. And then if you click on the chart and you move to any one of these dots, you can see that for every dot that exists, it tells you how many neutrons. So this dot has 37 neutrons, and then the 30 up above there tells you how many protons it has. If you go someplace where there isn't a dot, you don't get a reading at all because it can't tell you the coordinates of that point. For the most part, when I want to work with the chart of stable nuclides, I use the digital version just because I have the ability to locate every point very, very precisely. So that's the first link on our Schoology page, and that link will stay there as the lead link on the Schoology page until we're done with our nuclear science unit. We can connect this to our study of the AZX notation by zooming in on just this region up here of the chart of stable nuclides, the 10 by 10 region that goes from protons between 80 and 90 and neutrons between 120 and 130. So here's a zoomed in region of this little piece right up here, just to help us understand the connection to what we did a couple of days ago. What I've done is I've taken the little blue dots, which are highlighted here, and I've shaded them gray. So here's the little upside down L, and then the funny little zigzag thing. And then all of this white region is all the spaces up here that don't have a little dot. Of the 100 possible things you could make using anywhere from 80 to 89 protons and 120 through 129 neutrons, only 10 of those actually make a nucleus that's going to be stable or not radioactive. I've then gone through and I filled in the AZX symbols for these. So down here we have mercury because it's element number 80 and mercury's number 80. So all of the things in this column represent mercury atoms. And this mercury has 80 protons and 120 neutrons, so it has a mass number that's the sum of those things, or 200. And so you can look at the AZX symbol for all of these, and you can see that the mass number is always just the sum of the coordinates of the point, and the number of protons tells you which element is represented by each little box. And so that's a zoom in of here that helps kind of see the relationship between the AZX notation and what you can read off of your chart of stable nuclides. The usefulness of this chart is really twofold. First of all, it tells you whether a particular isotope of an atom is radioactive or not. And the second thing it tells you is if decay is going to happen, what's going to take place. The first type of decay you've become familiar with is alpha decay. Alpha decay occurs for elements that are up beyond the band of stability. These elements are too large. They have too many protons and too many neutrons. And as you saw in your movie and your study of alpha decay, the solution to being too large is to lose 2 protons and lose 2 neutrons. And this process is called alpha decay. And that's the type of decay that uranium undergoes. The nucleus is too big. It just needs to get rid of some particles. But there are 2 other possible problems with a nucleus. In this region over here, the nucleus isn't too large. However, a nucleus someplace like this has too many neutrons or not enough protons. We know that because if we were to slide downward and lose neutrons, we could land at something stable. Or if we were to slide sideways and gain protons, we would land at something stable. So for nuclides in this area of the chart that don't fall on a dot, their problem is they have too many neutrons and not enough protons. The solution is to turn a neutron into a proton, therefore losing 1 neutron, gaining 1 proton, the net effect being it moves down 1 and scoots 1 to the right, and that can put it onto one of these points. This process is called beta decay, and it's one of the types of decay that you're going to learn about today. The opposite problem would be for nuclides that are down here. These nuclides have a problem of having too many protons and not enough neutrons. If a radioactive nuclide is over here, losing protons, moving this way, or gaining neutrons, moving upward, would get back to the band of stability. The solution to this is to turn a proton, which you have too many of, into a neutron, which you have not enough of, and this process is called positron decay. That'll be the second type of decay you learn about today. There is a 4th type of decay. We have alpha, beta, and positron. You've learned about alpha decay. You're going to learn today about beta and positron decay. But the 4th possibility is something called gamma decay. Gamma decay is energy that's released when one of the other decays has occurred and the nucleus is now arranged in an unstable way. This type of decay doesn't show up on the chart because it's emission of energy rather than just emission of a particle. One of the ways I tell people to think about gamma decay is to imagine going to Walmart in the spring and buying one of those great big colorful balls that little kids like. They have a great big tower of balls, and you reach in and you grab one of those out of the middle. The rest of the balls in the stack are now unstable, and they sort of jiggle and tumble back into a more stable conformation. The same thing is true when a nucleus loses a radioactive particle. The remaining protons and neutrons may be arranged in a way that's not stable, and as those protons and neutrons kind of jiggle and shift into a new, more stable position, the nucleus gives off energy, and we call that energy gamma radiation. It's a very high energy photon that's emitted from the nucleus as the nucleus arranges itself in a much more stable way. From here, you're going to watch two more videos from Tyler DeWitt, one about beta decay and one about positron decay. Learn how to write the nuclear equations for that, and then watch a very brief video about gamma decay. And then using the things that you've learned, you're going to write the decay chain, or the entire process that takes you from the uranium dragon all the way into the little lead dragon that curled up and went to sleep in the fire.